A very good morning, afternoon, or evening to everyone. I'm Kenneth, and on behalf of my co-authors, it is my pleasure to present our work in the 2023 International Conference on Acoustics, Speech, and Signal Processing. Our work concerns a multimodal method for the prediction of effective responses to augmented urban soundscapes. The main application of our work is to allow an automatic selection of sounds, also known as maskers, to add or otherwise augment to real-life urban soundscapes to improve attributes such as the perceived pleasantness or acoustic comfort. The main novelty of our work lies in the extensible multimodal fusion methods to include additional information pertinent to perception, such as visual information or information related to the listener. Using participant-linked information in this way significantly improves model performance in terms of mean squared error in the prediction of ISO pleasantness. In short, as the title of the presentation suggests, we have developed a model to perform autonomous soundscape augmentation with multimodal fusion of visual and participant-linked inputs. With that, allow me to elaborate on the background and motivation behind our project. We are working under the paradigm of a soundscape being an acoustic environment as perceived by a person or people in context. This follows the definition provided by the International Standard for Soundscapes ISO 12913. Consequently, augmentation involves adding maskers to existing soundscapes to alter their perception. For example, we could add the sound of a bird to an existing soundscape beside a noisy road to improve its overall perceived pleasantness. In practice, this addition can be done via headphones or speakers. For this project, we return to the definition of a soundscape and focus on the two words person and context. This implies the importance of considering non-acoustic factors when analyzing or predicting perceptual quantities related to soundscapes. The first possible factor is the visual environment. For instance, in the study illustrated by the figures on the right side of the slide, the visual environment with an added green hedge blocking the view of the road had a higher relative preference score when both were combined with the exact same audio clip. Other important factors to consider are demographic factors such as the participant's age, as well as environmental factors such as the ambient temperature. In light of this, we would expect that for models relying purely on acoustic information, incorporating additional information from relevant non-acoustic modalities would improve their performance. Hence, for this project, we investigate the multimodal idea on an attention-based model which we call a Probabilistic Perceptual Attribute Predictor, or PPAP for short. I will first describe the acoustic-only version and then elaborate on how we extended it to be compatible with multiple modalities. As I explained earlier, in soundscape augmentation, we add maskers to existing soundscapes. So we begin by considering their spectrograms separately. In practice, the base soundscape is the ambient acoustic environment, so we assume no gain control over it. However, we can control the gain of the added masker, for example, by adjusting the volume of a playback system. So we include the log gain as an auxiliary input to the PPAP. The acoustic-only PPAP then extracts features from the base soundscape and masker separately, and then performs augmentation in the feature space to output augmented soundscape features with the log gain as a calibration factor. Considering the base soundscape, masker, and augmented soundscape features as keys, queries, and values to any compatible QKV attention block, the PPAP finally predicts parameters of a random distribution modeling a given perceptual attribute for that augmented soundscape, such as its perceived pleasantness. This gives the PPAP a probabilistic nature, and we train it with a corresponding loss function, which is the log probability of the observed ground truth given the predicted distribution parameters. Now, we modify this architecture into what we call a contextual PPAP that encompasses multimodal inputs. As an example for this study, we consider contextual information from the listener, such as their demographic, as well as images from the visual environment matching the acoustic environment of the base soundscape. This is inspired from the definition of soundscape as perceived by a person or people in context. As with the acoustic-only PPAP, we first extract features from the new modalities and add in virtual switches that allow us to choose independently whether to include them as additional inputs. We then need to address how to fuse these multimodal features with the acoustic-only PPAP in a sensible manner. For this study, we propose three modes of fusion, which we refer to as early, mid-level, and late fusion. In early fusion, we treat each mode as independent channels of information in the feature augmentation block f of g, and stack them together as input into a convolutional block. In mid-level fusion, we only use the log gain corresponding to the acoustic modality in the feature augmentation block f of g. and concatenate the information from all nodes at the output level. And lastly, in late fusion, we use the same idea as mid-level fusion, but we concatenate the information from all modes after the output level of the acoustic-only PPAP. To validate our proposed method, we ran experiments on the different modalities and fusion modes on a common dataset that we previously collected. This is the aroused dataset consisting of audio-visual stimuli configured in a manner that allows for 5-fold cross-validation. Each stimulus in the dataset is an augmented soundscape paired with a ground truth set of responses to a selection of perceptual attribute scales provided by study participants. For our validation experiments, we use the attribute ISO pleasantness, which takes values from -1 to +1. The set of responses is also publicly accessible at the URL shown on the slide. For the experimental setup, we varied all combinations of modalities and fusion methods that we described earlier in the presentation, and a visual summary is shown in the table on the right of the slide. As a baseline reference, we also run the experiments on the acoustic-only PPAP, which is not multimodal in nature. We use a common dot product attention block for all variants of the contextual PPAP, as well as the same loss function corresponding to the log probability of a normal distribution for training in order to allow for a consistent experimental setup. We ran 10 runs for each investigated variant and aggregated the results in terms of the mean squared error in prediction. The table on the right of this slide shows a summary of the results. We did a Kruskal-Wallis test with Bonferroni correction to verify if any changes in performance with respect to the baseline were indeed statistically significant. We can observe that there were significant improvements in performance when participant-linked information was used as additional multimodal inputs, with the greatest improvement in the late fusion method. Adding in the visual modality also gave improvements in the performance, but the improvements were not statistically significant. However, using both the visual and participant-linked modalities together potentially leads to significant worsening of performance. This could be a conflict in the visual modality as an objective characteristic of the environment, with the participant-linked modality related to the subjective perception of the environment. Hence, the optimal fusion methods might differ for different modalities, and the architecture might need to be tweaked to accommodate this in the future. With that, I have come to the end of my presentation. If you have any questions or would like to discuss our work in more detail, please feel free to come to our poster session on the 6th of June at 10:50 AM, or please feel free to drop us an email as well. Thank you so much for your attention.